Good afternoon, students. This is Aravind, Assistant Professor, Department of DBSIT, KAVALI. So, in the previous class, I discussed about some voltage regulation methods to determine the voltage regulation of an alternator, that is direct loading method. And next, coming to indirect methods, in the previous class, I discussed about EMF method and MMF method. And now in this class, I'm going to discuss voltage regulation determine the voltage regulation by using ZPF method, that is zero power factor method. Okay, coming to the topic, that is, so ZPF method is also called as Poisson triangle method. So we're known that the ZPF method is also called as Poisson triangle method, and this method is based on the separation of armature leakage reactance drop and armature reaction effect. Okay, so the armature leakage reactance XL is called Poisson reactance. Hence, this method is called Poisson reactance method. Okay, next, we will consider some assumptions as similar to the previous two methods. That is for EMF and MMF method. Here also I am taking assumptions. That is, here also the saturation effect is neglected. And coming to the second assumption, that is leakage reactance XL and armature reaction reactance XA are considered separately. This is the main case we are using here. That is, this method is based on the separation of armature leakage reactance and next reaction armature leakage reactance drop and armature reaction effect. Okay, so to determine leakage reactance, that is XL, and armature reaction MMF separately, two tests are performed. One is open circuit test and another one is zero power factor test. So in the previous methods, we seen that two methods also there, that is open circuit and short circuit. Now in this method, we are using two tests, that is open circuit test and zero power factor test. And coming to the first one, that is open circuit test. So this is the diagrammatic representation of open circuit test in a ZPF method. So here I am taking one prime mover. So it is used to driven the alternator at a rated speed. Okay, so here I am taking star connected armature winding. So it consists of one voltmeter. So this voltmeter is used to measure the open circuit voltage. And next we have the field winding. The field winding consists of one ammeter. So this ammeter is used to calculate the field current. And next this ammeter is connected to the field rheostat or potential divider. Okay, this is used to vary the flux. Okay, and next we are using some DC supply through the switch. Okay, and next here we are using purely reactive load. Okay, purely reactive load, and that purely reactive load consists of an ammeter. So this ammeter is used to calculate the armature current, and here I am connecting one switch in between stator armature winding and purely reactive load. Okay, next coming to the explanation of this test. So open circuit test is done step by step from the following points. So here we are using some points to explain the open circuit test, how it is done. Okay, so firstly, we are taking the switch S is open condition. Switch S is open. So that means the alternator is made to rotate using prime mover at synchronous speed. So I already said this point. The prime mover is used to drive the alternator at synchronous speed or constant speed, and same speed is maintained constant throughout the test. Okay, so here the alternator is made to rotate using prime mover at synchronous speed, and the same speed is maintained constant throughout the test. Okay, so coming to the third point, that is the excitation value is changed using potential divider. So I already shown the potential divider diagram. So it is connected to the field winding through an ammeter. So here I am, if you want to change the excitation value, we are using potential divider from 0 up to rated value. From 0 to minimum, that is 0 means minimum value, minimum to rated value in a definite number of steps. Okay, and next the open circuit EMF is measured with the help of voltmeter. Open circuit EMF is measured with the help of voltmeter, and next the readings are tabulated. So you already know, if we If already taken these values means we have to tabulate these readings, that is a open circuit EMF value from the voltmeter we have to tabulate. And next coming to the fourth one, here I am taking a graph of field current and open circuit voltage, okay, per phase is plotted to some scale, that is open circuit characteristics. So here the graph is drawn between field current and open circuit voltage per phase. It gives the open circuit characteristics of ZPF method. And next coming to the zero power factor test. This is the second test we are using for the zero power factor method. So here to conduct zero power factor test, the switch S is kept closed. Okay. For open circuit test, we are open the switch. For a zero power factor test, the switch S is kept closed. Okay, due to this, a purely inductive load gets connected to an alternator through an ammeter. So I already seen the diagram, I already shown the diagram. So the diagram consists of a purely reactive load, and the purely reactive load consists of an ammeter and the connection of purely reactive load and in between purely reactive load and star connection of armature winding, we have one switch. So here a purely inductive load gets connected to an alternator through an ammeter. That means a purely inductive load has power factor of cos 90 degrees. Okay, that is zero lagging. Hence, this test is called zero power factor test. Okay, and next the machine speed is maintained constant at its synchronous value. Okay, the load current delivered by an alternator to purely inductive load is maintained constant. Okay, the load current delivered by an alternator to purely inductive load is maintained constant at its rated full load value by varying the excitation and by adjusting variable inductance of the inductive load. Okay, that is purely inductive load or reactive load. Okay, note that due to pure inductive load, an alternator will always operate at zero power factor lagging. Okay, note that due to purely inductive load, an alternator will always operate at zero power factor lagging. And next coming to the point, that is the below is the graph of, so here also we are taking one graph, so that gives the zero power factor uh, characteristics. So here the we are taking the graph of terminal voltage against excitation, terminal voltage against excitation when delivering full load zero power factor current, when delivering full load zero power factor current. So one point for this curve is zero terminal voltage and the field current required to deliver full load short circuit armature current. Okay, that is for the short circuit condition. Okay, so one point for this curve is zero terminal voltage and the field current required to deliver full load short circuit armature current. Okay, so while other point field current required to obtain rated terminal voltage while delivering rated full load armature current. This is also one more another point. Okay, here the field current required to obtain rated terminal voltage while delivering rated full load armature current. Okay, and next with the help of these 2 points, the zero power factor saturation curve can be obtained as firstly plot open circuit characteristics on graph paper. Okay, firstly we will take the open circuit characteristics, that is the graph between field current and open circuit voltage per phase. And next coming to the second point, so here plot the excitation corresponding to zero terminal voltage. Okay, plot the excitation corresponding to zero terminal voltage, that is short circuit full zero power factor armature current, full zero power factor armature current. So this point is shown as A in the diagram with the which the x-axis. Another point is the rated voltage when the alternator is delivering full current at zero power factor lagging. This point P is shown in this diagram. So this is the characteristic diagram for the ZPF method. So here this point. So actually in the x-axis we have field current and in the y-axis we have terminal voltage and induced EMF per phase. Both are same. Okay. So here I am indicated with some Here I am drawing two curves. So the first curve, that is O, R line, gives the OCC characteristics of the ZPF method, and A, P. So this curve is gives the full load zero power factor saturation curve. Okay, these two. Next, so here, firstly we drawn open circuit characteristics, and next we are drawn the excitation corresponding to zero terminal voltage, that is short circuit full zero power factor armature current. This point is shown as A in the below figure, which the x-axis. Okay. Another point is the rated voltage when alternator is delivering full current at zero power factor lagging. So here it gives the P point. So this one, A to P. Okay. So this is rated voltage per phase. Okay, here we have one triangle. This is Poisson triangle. I will explain this diagram very deeply by using some points. Okay, if you have the time, please draw this diagram. Okay, so here I am taking draw the tangent to OCC through origin, which is line OB as shown dotted in below figure. This is called A line. So if you observe this diagram, we have a tangent to OCC through origin, that is O. So here we have drawn a tangent line with a dotted line. This one is also called as air line. Air line. So air line. So here draw the tangent to OCC through origin, which is line OB. Okay, this one OB. This is line OB shown dotted in below figure, that is called air line. And next draw the horizontal line PQ parallel and equal to OA. So here we have to draw the horizontal line PQ parallel to OA. So this one. PQ parallel to OA. So this one. Okay. This one is OA. Here I am drawing PQ line horizontal to the parallel to the OA line. Okay. Parallel and equal to OA. And next from the point Q. So from this point. So from the point Q, draw the line parallel to the air line. So here in the first point, I said that here we have one air line. So that air line is drawn from the origin, that is O point to B point. Okay. So here from the point Q, draw the line parallel to the air line. So from the point Q, I am drawing one line. Okay, that is parallel to the air line, which intersects OCC at point R, which intersects the OCC curve. This one is OCC curve. First curve is the OCC curve. So here the Q point is started here and it touches to OCC curve. This point is represented with R. Okay. So air line which intersects OCC at point R, join RQ and join PR. So after that we have to join RQ and PR. RQ and PR. So this will gives the triangle PQR is called Poisson triangle. That one is called as Poisson triangle. So next from the point R. So here if you take from the point R, what we will is drop a perpendicular on PQ to meet point S. So from point R, drop a perpendicular on PQ to meet at point S. To meet at point S. Where is the point? This one. Okay. So to meet the point at S point. Okay. This one. Here we have. Okay. This dotted line. PQ, we have the Poisson triangle, that is the PQR. So here we have one thing, that is from the point R, drop a perpendicular on PQ to meet at point S. So the zero power factor full load saturation curve is now constructed by moving triangle PQR. So here I am moving that PQR triangle. Okay, so that R remains always on OCC. R remains always on OCC and line PQ always remains horizontal. So here I will represent with that one represented with the dotted triangle. So this one. Actually we have PQR, this is the Poisson triangle, and here we have dotted line triangle, same as this is the Poisson triangle. So that is P dash, Q dash, R dash and S dash. So this is the diagram So that is for the zero power factor full load saturation curve is now constructed by moving triangle PQR. Okay, so that R remains always on OCC and PQ always remains horizontal, but the dotted triangle is shown in the diagram. So that consists of the points P dash, Q dash, R dash and S dash. Okay, if we noted that the Poisson triangle once obtained is constant for a given armature current and hence can be transferred as it is. Okay. And next, through point A, draw a line parallel to PQ, meeting OCC at point B. So here I am taking point A. So through point A, draw a line parallel to PR. Okay, this one. Okay, through point A, draw a line parallel to PR that meeting at point B. So PR that meeting at the point P, point B, sorry, point B. Where is the point? This one. Here is the B. Okay. Next, draw a perpendicular on OA to meet it at point C. So from that one, to draw a perpendicular on OA to meet at point C. So here OA and it meet at point C. So this one. Okay. So in the horizontal line we have OA CB points. So here I am drawing a perpendicular line. Okay. Perpendicular line OA to meet it at point C. So here we have triangles OAB and PQ are similar triangles. So here we have two triangles. One is OAB and we have PQR. Both are same. Both are same. So the perpendicular RS gives the voltage drop due to armature leakage reactance. The perpendicular RS gives the voltage drop due to armature leakage reactance. So here we have RS line. So this one gives the drop due to armature leakage reactance, that is IXL. And next the length PS gives field current. Here we have PS length also, this one. So this length gives the field current necessary to overcome the demagnetizing effect of armature reaction at full load. Okay. Next, the length SQ. So these are from the Poisson triangle only. So RS, PS and SQ. So the length SQ represents field current required to induce an EMF for balancing leakage reactance drop RS. Leakage reactance drop RS. So these values can be obtained from any Poisson triangle such as OAB, PQR and so on. Okay. And next, so armature leakage reactance can be obtained as by using this formula, that is I of, that is for L of RS, that is equal to L of BC IA phase for full load into XL phase. So from this one I am writing XL phase is equal to leakage reactance, that is XL phase is equal to L into RS or L into BC by IA phase into F IA phase, that is armature current per phase. This is nothing but the post-shear reactance. XL phase is equal to L of RS or L of BC, that is length of RS. L of BC means length of BC, that is the BC points and RS points. Length of RS and length of BC by armature current per phase at full load. This is nothing but the post-shear reactance. Okay. And next, use of Poisson reactance to determine regulation of alternator, that is voltage regulation. So to determine the regulation using Poisson reactance, that is the previous formula, that is XL is equal to length of RS into length of BC by XL, IA phase. Okay, so to determine regulation using Poisson reactance, draw the phasor diagram using following procedure. So if we want to determine the regulation using Poisson reactance, we have to draw the phasor diagram using following some procedure. In that one, first one is draw the rated terminal voltage V phase as reference phasor. If you see this diagram, will understand. So here I am taking voltage as phasor. Okay, reference phasor. Next, depending upon at which power factor the regulation is predicted, depending upon at which power factor the regulation is to be predicted, draw the current phasor I phase lagging or leading V phase by angle alpha. So this is depend upon the power factor type of power factor, that is inductive, capacitive or unity. Okay, so depending upon the power factor, the regulation is to be predicted. Based on this, draw the current phase or IA phase lagging or leading V phase by angle phi. Okay, and next draw I phase and RA phase, IR voltage drop to V phase, which is in phase with I phase, while the voltage drop I phase to XL phase is to be drawn perpendicular to I phase R phase vector, but leading I phase R phase at the extremity of V phase. Extremity of V phase. Okay, if you see the diagram, you will understand. So what we are doing is, firstly we draw voltage phase, that is V phase as a reference phasor, and next depending upon the power factor, that means load, the regulation is to predicted. That means if it is a leading power factor, we have to take the current phasor leading V phase, I phase is leading V phase, and if it is a inductive load, we are taking I phase lagging V phase. Okay, depending upon, we have to draw that one. And next, in the next point, we are taking the voltage drops. So here, first we will draw I phase, RA phase voltage drop to V phase, that is the reference phase, which is in phase with I phase. That is in phase with I phase, while the voltage drop I phase XL phase is to be drawn perpendicular to the I phase R phase vector, but leading I phase RA phase at the extremity of V phase. Okay, so this one. So here I am taking voltage phasor, that is V phase, this one. O2 I phase, we have one thing. So V phase, this is the reference phasor, and next we will take the type of the power factor. We are taking the I phase. Here I am taking I phase leads V phase at an angle phi. Okay, and next I am drawing the drops. So that is IE phase, RE phase, and I phase, XL phase. So these are indicated with B point and C point we have. Okay. Next, the R phase is to be measured separately by passing a DC current and measuring the voltage across armature winding. So here I am taking R phase, so it is to be measured separately by passing a DC current and measuring the voltage across armature winding, while XL phase is Poisson reactance obtained by Poisson method. So here R phase is to be measured separately by passing a DC current and measure the voltage across armature winding, while XL phase is a Poisson reactance obtained by the Poisson method. That is the formula: XL phase is equal to length of RS into length of BC by IL phase. Okay, here I am taking phasor sum of V phase rated and drop I phase, RA phase, and I phase, XL phase gives the EMF, which is say even phase. So here even phase is equal to V phase plus I phase, RA phase plus I phase, XL phase. Okay, this is the phasor sum. Okay, next obtain the excitation corresponding to even phase from OCC, which is drawn. Let this excitation be FF1. This is excitation required for inducing EMF, which does not consider the effect of armature reaction. Okay, and the field current required to balance armature reaction can be obtained from Poisson triangle method, which is say FAR. So FAR is equal to I into P, that is the length of PS is equal to length of AC. Okay, or current of PS point and AC point. The total excitation required is the vector sum of FF1 and FKR. This can be obtained exactly similar to the procedure used in the MMF method. Okay. Next, draw vector FF1 to some scale leading even phase by 90 degrees and add FAR to FF1 by drawing vector FAR in phasor opposition to I phase the total excitation to be supplied by field is given by Fr. So this is the procedure we maintain to draw the phasor diagram. So this is the complete phasor diagram for the those points. Okay, this is the complete phasor diagram. So here we are using Fr and Fer. Okay, next FF1 like this, and even phase, E phase, armature reaction drop. Okay, these are the points we are taking. And next, once the total excitation is known, which is Fr, that is Fr, the corresponding induced EMF, that is E phase, can be obtained from OCC. Okay, so this E phase, that is induced EMF, lags Fr by 90 degrees. And next, the length CD drops due to armature reaction. The length CD drops due to the armature reaction. Draw perpendicular from A and B on current phasor meeting at points G and H respectively. A and B and G and H. Okay, we get triangle OHC as right angle triangle. So here we have OHC. So this is the triangle. Okay. And next, hence E1 phase can be determined analytically also. Once E phase is known, the regulation of alternator can be predicted as percentage of regulation is equal to voltage regulation is equal to E phase minus V phase by V phase into 100. So here E phase is the induced EMF for full load minus V phase by V phase into 100. No load E phase. Okay. Next, ZPF method takes into consideration the armature resistance and leakage reactance voltage drops as EMF quantities and the effect of armature reaction as MMF quantity. So this is the reality. Hence the results obtained by this method are nearer to the reality than those obtained by synchronous impedance method and ampere turns method. Okay, the only drawback of the ZPF method is that the separate curve for every load condition is necessary to plot if Poisson triangles for various load conditions are required. This is the only drawback we have for the GPF method. And assumptions made in the Poisson method is, I already said these points and again repeating this one. So some assumptions are made in the Poisson method which is listed below. So here in the entire calculation procedure of Poisson method, the armature resistance is neglected, but practically armature resistance is very small and hence this assumption does not cause significant error in the accuracy. And second one, in Poisson method, a zero power factor test is required to be done. But practically when inductors are used, a perfect zero power factor cannot be achieved. Next, consider the graphical interpretation of Poisson triangle shown in the figure. So here also this is the copy paste of the previous one, that is Poisson triangle. So in the x-axis we have, y-axis we have our terminal voltage and induced EMF per phase. So here I am drawn two curves. One is for open circuit curve, open circuit characteristics, and another is for full load zero power factor saturation curve. So here we have Poisson triangle that is represented with PQR triangle, and another one we have a dotted line triangle. This is also same as Poisson triangle, and we have OAB triangle. This is also equal to the Poisson triangle. Here we have on air line, okay, and rated V phase value is also there. So this is the graphical interpretation of Poisson method. And next in this graph, the distance RS, R dash, S dash and BC are assumed equal. So in the graph we have RS, that is this one, RS, and R dash and S dash, and next we have BC are assumed equal. And next this represents the voltage drop across the leakage reactance, which is IA phase full load into XL phase. Okay, this indicates that the point P in the zero power factor method at point A in the short circuit test represent the same leakage reactance of the machine. But this is not true as the excitation under short circuit condition is OA, while the for point P is OA as shown. Okay, next, now the excitation OA dash is much higher than OC, and hence point P corresponding to saturated conditions represent larger leakage flux, which in the method assumed unchanged. Okay, Hence, practically the leakage reactance corresponding to saturated conditions is higher than that assumed in the method. So this introduces the error in the calculations. Okay. So that's all. This is the explanation for the JPF method. This is very important in the examination point of view for JNTUA. Okay. Thank you.